All right, hello and welcome. Today we are diving into something pretty mind-bending from the world of quantum geometry. It's a theory that asks a truly radical question. What if everything we think is fundamental, space-time, matter, all of it, isn't fundamental at all? What if it all just emerges from one single incredibly simple drive for self-preservation? Let's get into it. You know the picture we all learn in school, right? It's pretty straightforward. You've got matter, which is all the stuff. That stuff moves around on a sort of stage called space-time, and everything is controlled by a set of rules, the fundamental forces, like gravity. It's a picture that works, it's been tested, and it makes sense. But what if that whole picture is just the surface? You know, a convenient story we tell ourselves that hides a reality that's so much deeper, so much more connected, where the lines between matter and space and forces just completely blur away. And that gets us to the absolute core question of this whole explainer. What if all the incredible complexity we see out there, from a massive, swirling galaxy all the way down to a single proton, what if it all springs from one fundamental drive? The drive for things to simply, stay as they are. Okay, so to really get our heads around this, we've got to start right at the beginning with the theory's most basic building blocks. These are a couple of new ideas that kind of redefine how we even talk about reality itself. So the first piece of the puzzle is something called a context. Now, the easiest way to think about this is as a single, indivisible moment of observation. It's one measurement, one interaction. It's one specific point of view on the universe. It's like the absolute smallest, most basic pixel of information you can possibly have. And here is the one single rule that this entire theory is built on. Every single one of those contexts has a built-in tendency to preserve itself. It pushes back against being changed. Think about a spring, right? You stretch it, it wants to snap back. According to this idea, that simple resistance is the fundamental engine driving our entire reality. Kind of wild, huh? Now, of course, not everything resists change with the same amount of oomph. And the theory has a name for that: stiffness. Some of these contexts are incredibly tough, super resistant, while others are way more flexible. And the key thing here is that this isn't just some vague concept. Stiffness is a real, measurable quantity that tells you exactly how resilient any particular piece of reality is. Okay, so we've got these simple ideas, these little individual viewpoints that just don't want to be changed. But how in the world do you get from that to a universe packed with galaxies and planets and everything else? Well, this is where the theory gets really, really elegant, by connecting that one simple rule to the grand geometry of both space and force. So here's the puzzle, right? How can this one single principle, self-preservation, give rise to two things that seem completely different? On one hand, you have the vast, sweeping stage of space-time, and on the other, you have the very specific, internal rules that govern how tiny particles interact. And the answer is just beautiful. It all comes down to what kind of change is being resisted. So when a whole network of these contexts resists being moved around or rearranged, an external change, what we experience is gravity. It's the curvature of space-time itself. But when a context resists having its internal properties messed with, things like the color charge that glues quarks together, that's what creates the geometry of the fundamental forces, like the strong nuclear force. It's the same principle, just working in two different ways. And this right here is the core insight. It means space-time isn't some passive background, and forces aren't just a random set of rules. No, they are both geometric results of the exact same fundamental drive, the universe's tendency to keep itself the way it is. Okay, so that's all pretty abstract. Let's make it way more concrete. How does a theory like this explain something we think of as solid stuff, like a proton or a neutron, what physicists call a nucleon? Well, here's the twist. In this model, a particle isn't a tiny solid ball. It's not a thing at all. It's what the paper calls a self-preservation condensate. I want you to think of it like an incredibly tight, unbelievably stable knot that's been tied in the very fabric of reality. It's a pattern that's become so stiff and self-reinforcing that it acts just like a single persistent object. So what does it take to form one of these stable knots? Well, the theory basically gives us a recipe with 4 key ingredients. First, you start with a region of these contexts. Next, you arrange them into the most stable, most efficient pattern possible. Then, that pattern has to become incredibly stiff, so resistant to change it behaves like a solid object. And finally, all of its internal forces, like its color charge, have to cancel each other out perfectly, making it totally stable and neutral. And when you get all four of those conditions, something amazing happens. And that's the big payoff. When you have a pattern that meets all of those criteria, when it's stable, incredibly stiff, and internally balanced, that pattern is what we see as a nucleon. It isn't a fundamental thing, it's a condition of maximum stability. So let's just pull all the way back for a second and think about the absolutely incredible picture this theory paints. I mean, if this is even close to being right, it's not just some small tweak to physics. It's a complete rethinking of what reality actually is. The huge takeaway here is that all those old divisions we used to make, they're just gone. The stage of space-time isn't separate from the actors, the particles, and neither of them are separate from the script, the forces. They are all just different expressions of one single, underlying geometry that is constantly, always working to preserve itself. And honestly, this quote from the source material just says it perfectly. Particles like nucleons aren't the universe's tiny little Lego bricks. They're more like whirlpools, stable, emergent patterns that just naturally arise from the deep-down dynamics of this one integrated geometry. Which, of course, leaves us with a final, absolutely fascinating question. If a proton is just an incredibly stable pattern, what else could be? Life itself? Consciousness? It suggests that maybe the deepest secrets of the universe aren't about finding the smallest possible things, but about understanding the rules that allow stable, complex, beautiful patterns to emerge and to last.